The Milky Way is not a line in the sky. It has no sharp border, no final edge where the stars simply stop. Instead, it fades, quietly, gradually, into a haze of drifting worlds, dark matter, and ancient starlight stretched thin across the night. Even as you sit here, breathing gently, you're inside a structure so vast that its true boundaries remain partly hidden, wrapped in distance and time. Tonight, we'll drift through that mystery with calm precision, exploring how far our galaxy truly reaches, and why the answer depends on how you choose to measure a place that has no walls. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm voyages alive, and it means more than you know. Now we drift into the first ideas, 15 quiet chapters waiting like distant lights. Part 1. Where does a galaxy truly begin? If you could float just outside the solar system and look back toward the Milky Way, you wouldn't find a border. You'd see a gradient of stars growing denser toward the center, like dust thickening in a beam of light. The beginning of a galaxy is not a line but a slow gathering of gravity, where scattered stars start to feel each other's pull and space becomes structured rather than empty. This is the quiet truth hidden behind every photograph of the Milky Way. Galaxies don't start the way continents or oceans do. There is no sharp coastline, no sudden wall of light. Instead, there's a gentle rise in order, a subtle shift in density, a place where empty space begins to feel less empty. Even from your vantage point, floating far above the ecliptic plane, the shape of the Milky Way wouldn't reveal itself all at once. It would emerge slowly, star by star, like a soft glow rising from the horizon. Astronomers call this region the outer disk, a faint, sprawling extension of the galaxy that lies far beyond what human eyes can see from Earth. In maps made from radio telescopes, it forms a vast, dim structure of hydrogen gas, stretching outward tens of thousands of light years past the bright spiral arms. If your eyes could detect those wavelengths, the galaxy would appear much larger than the familiar band of starlight we see at night. But the deeper question remains: when does this become a galaxy? To understand that, you must first imagine space without structure. Imagine drifting through a region where stars are so far apart that gravity barely whispers between them. In such a place, a star can live its entire life without feeling the presence of another. The universe is full of these empty realms, dark reaches between galaxies where the nearest neighbor may lie millions of light years away. The Milky Way begins where that isolation ends. As you drift closer, you begin to sense a pattern. Far-flung stars start to share a common motion, following the same broad gravitational curve. Their orbits align, not perfectly, but enough to reveal a shared history. This coherence, the way stars move together, is the first sign that you have entered a galaxy's outskirts. Even if the stars remain sparse, gravity has woven them into a single system. It's here that the Milky Way quietly starts. Scientists often define this beginning using measurements of orbital velocity. By tracking how fast stars move around the galactic center, astronomers can determine whether they are bound to the Milky Way or drifting independently through intergalactic space. If a star circles the center faster than the escape velocity, it belongs to the galaxy. If not, it merely passes through. This boundary is neither sharp nor permanent. It changes over time as the galaxy grows, merging with smaller galaxies, absorbing their stars and stretching outward as it reshapes its gravitational field. If you could watch the Milky Way unfold over billions of years, like a cosmic time lapse, you would see it breathe, expanding slowly as streams of stars rain in from the surrounding universe. But even this is not the true beginning. To find that, you must look deeper, beyond the motions of individual stars, beyond the visible structures of spirals and clouds, into the quiet architecture of dark matter. The Milky Way is wrapped inside a colossal dark matter halo, a sphere of invisible mass that stretches far beyond the disk of stars. And it is this halo that defines the galaxy's skeleton, shaping every orbit, every arm, every cluster of light. Where the influence of this halo first becomes noticeable, where its gravity begins to gather the smallest particles into a cohesive structure that is the earliest root of the galaxy. The dark matter halo extends nearly 1,000,000 light-years in every direction, dwarfing every visible part of the Milky Way. Compared to it, the glowing disk we see in photographs is just a thin, bright ripple on the surface of a much larger sea. So perhaps the galaxy begins not where the first stars cluster, but where the first faint arcs of dark matter start to bend the paths of passing particles. And yet, there's another way to define a beginning. Some astronomers argue that a galaxy starts wherever starlight becomes common enough to shape space into a recognizable pattern. In this view, the earliest sign of the Milky Way is the thick disk, a region slightly above and below the main plane of the galaxy, where ancient stars drift in long, looping orbits. These stars are older than the Sun by billions of years. They were already burning when the Milky Way was still assembling its spiral arms, still forming the structures we now see so clearly. If you could hover among these stars, the galaxy would feel ancient and quiet, a world before the world you know. Their slow orbits trace the early geometry of the galaxy, hinting at a time when the Milky Way was more chaotic, less like the elegant spiral we imagine, and more like a vast cloud slowly learning how to rotate. Still, there is an even more intimate beginning. Some astronomers define a galaxy's start through chemistry. They ask, where do we find the first elements forged in earlier generations of stars? Where does the presence of heavier atoms, carbon, oxygen, iron, begin to rise above the abundance found in the empty universe? In this view, the beginning of the Milky Way is not a location, but a transformation. It emerges wherever primordial hydrogen clouds first become enriched by the ashes of dying stars. These enriched regions mark the earliest star-forming rings of the galaxy, places where gravity collapsed gas into the first newborn suns, lighting up the cosmic dark. If you drifted there, the stars would look strangely pure, many of them containing almost no heavy elements at all. They carry the chemical memory of the early universe, shaped before the Milky Way had fully earned its name. So which definition is correct? The quiet truth is that galaxies do not have single beginnings. They have layers of beginnings, nested like the rings of a tree. A gravitational beginning, a chemical beginning, a structural beginning, a beginning of shared motion, a beginning of light. Each definition reveals a different face of the Milky Way, and each one traces the galaxy's story back to a different moment in time. As you drift closer, the faint stars begin to multiply. Gas clouds appear like translucent waves, their shapes guided by gravity. The rotation of the galaxy becomes noticeable, a slow, majestic turning spanning hundreds of millions of years for a single revolution. This rotation, too, is a boundary of sorts. It means you've entered the domain where the Milky Way's ancient spin overrides the random motions of intergalactic space. From here onward, every star, every cloud, every grain of dust is part of a larger choreography. And yet, even as the density increases, even as the spiral arms begin to take shape far ahead of you, the notion of an edge feels less meaningful. The galaxy does not claim space the way islands claim sea. It blends into the cosmos as though it were simply one expression of a larger pattern. As we move deeper, one question naturally follows. If a galaxy begins with a gradient, a slow rise in structure and light, then how far does the disk itself truly extend? Part 2. How wide is the galactic disk? You live inside. The disk of the Milky Way looks thin in images, but when measured carefully, it reveals a quiet immensity. About 100,000 light-years across, its spiral arms stretching like faint brushstrokes. If you could hover above it, the disk would appear both delicate and ancient, a rotating sheet of stars drifting through darkness with astonishing calm. From this vantage point, thousands of light-years above the galactic plane, the Milky Way doesn't look like a flat picture. It looks alive. The spiral arms curve outward in soft arcs, glowing with the faint bluish light of young stars. Dust lanes thread between them like dark rivers. And all of it turns together, ever so slowly, completing one full rotation roughly every 230 million years. If you watched patiently, you'd see that rotation like the turning of a wheel made of starlight. But the disk itself is far more than the graceful arms we sketch in textbooks. It is layered, it is structured, it is quietly immense. Astronomers describe the disk in two main parts, the thin disk and the thick disk, each with its own history written into the stars. The thin disk, the bright familiar layer where the sun resides, is only about 1,000 light-years thick, just 1% of its width. If the galaxy were scaled down to the size of a dinner plate, the thin disk would be thinner than a sheet of paper pressed to its surface. And yet, this slender structure holds most of the young stars we know. Blue giants, clusters, star-forming regions, nebulae glowing in gentle pinks and reds. It contains nearly all the raw material of stellar creation, hydrogen clouds, swirling dust, and the quiet turbulence that gives birth to new suns. But floating above it, extending farther, lies the thick disk, older, rougher, and broader. Its stars are ancient, many formed more than 10 billion years ago. Their orbits tilt slightly above and below the galactic plane, creating a gentle bulge of starlight that stretches several thousand light years thick. These stars carry the chemical memory of the early galaxy, containing fewer heavy elements, each one a relic from a time before the spiral pattern fully formed. Together, these two layers create a disk far wider than it is tall, a cosmic river frozen in rotation. Yet even this simple structure hides complexities. The Milky Way's disk flares at the edges, rising upward like the rim of a vinyl record warped by heat. Scientists once believed this distortion was unusual. Now they know it is common. Interactions with passing dwarf galaxies, the gravitational pull of dark matter, and the echoes of ancient collisions have slowly warped the disk over billions of years. In some regions, the outer disk rises nearly 10,000 light-years above the central plane, an enormous wave frozen in time. If you could drift just above the warped edge, you'd see the galaxy curve downward again toward the center like a bowl of light. This warping, subtle from a distance but dramatic up close, is one of the many signs that the Milky Way is not static. It breathes, it shifts, it carries the scars of encounters with smaller galaxies long since absorbed. The faint streams of stars pulled from these galaxies still thread through the halo, tracing quiet arcs across the sky. Each stream reveals a moment when the galactic disk was tugged, twisted, or reshaped. And yet, despite this history of disruption, the disk retains its overall symmetry. Its spiral arms remain intact, each one orbiting the center like a slow-moving tide. But how wide are these spiral arms themselves? Each arm stretches tens of thousands of light-years, but they are not solid. They are patterns, regions of denser gas and star formation that move through the disk like waves on the surface of the sea. As stars enter an arm, they brighten the pattern. As they drift out, they leave the pattern behind. The arm itself persists, not because the same stars remain inside it, but because the underlying gravitational wave continues to ripple around the galaxy. In this sense, a spiral arm is less like a physical branch and more like traffic on a highway. The pattern persists, even as the individual participants move through it. If you hovered above the disk long enough, millions of years, you would see these arms shift, stretch, and sometimes break. New segments form from the collapse of gas clouds. Old segments fade as star formation slows. The spiral is dynamic, always in motion, always reorganizing itself. And yet the width of the disk, roughly 100,000 light-years across, remains one of its most stable features. That number isn't exact. Some measurements place it closer to 120,000 light-years, others slightly less. But the general scale stays the same. 100,000 light-years from one end to the other. To put this in perspective, if the sun were reduced to a single grain of sand, the entire disk would span roughly the width of a continent, and you live inside it. You are not watching the disk from afar. You are within it, tucked into a small spur between two larger spiral arms, the Orion arm, a minor structure nestled gently between the Perseus and Sagittarius arms. From Earth, you cannot see the full disk. only the thin cross-section that arcs across the sky on a clear night. That band of stars is not a distant object, but the galaxy seen from the inside. Every time you look at the Milky Way overhead, you are looking along the plane of the disk, the same thin layer you call home. But its width is not experienced directly. The distances are too large, the light too faint, the dust too thick. Much of the disk is hidden from view, veiled by dark clouds that absorb starlight. Only with infrared telescopes, radio mapping, and careful measurements can astronomers trace its full shape. And what they find is both vast and delicate. The outer regions of the disk are far fainter than the inner ones, composed of lonely stars drifting in orbits that take hundreds of millions of years to complete. Some of these stars lie so far from the center that their motions feel almost hesitant, barely held by the galaxy's gravitational pull. They are part of the disk, yet already reaching into the halo, bridging the border between structure and emptiness. This boundary between disk and halo is not clear-cut. Like most galactic features, it is a gradient, a slow thinning of stars, a fading of light. The disk does not end because something stops it. It ends because space becomes too empty to be called a disk anymore. Even so, the rotation that holds the structure together remains one of its defining properties. The entire disk spins like a calm, ancient wheel. Near the center, stars orbit faster. Farther out, they move more slowly. But because of the influence of dark matter, an invisible mass that surrounds the galaxy, the rotation curve stays unexpectedly flat. Stars far from the center move faster than they should, as though guided by an unseen hand. This, too, defines the disk's width. Without dark matter, the galactic structure would unravel. Over billions of years, the outer stars would drift into space, leaving only a small, concentrated core behind. Instead, the disk remains wide, stable, and quietly immense. From your vantage point above the galaxy, the scale becomes undeniable. The disk stretches outward in every direction, thin but vast, fragile but enduring. It is wide enough that a single beam of light traveling at 300,000 kilometers per second would take 100,000 years to cross it. And you are inside that story. One star among hundreds of billions, one moment in a rotation older than any memory. As we continue drifting through this cosmic landscape, one question rises gently ahead. If the disk is this wide, this delicate, this structured, then what lies beyond its fading edges, where the spiral arms dissolve into darkness and the galaxy becomes something quieter still? Part 3. What lies beyond the spiral arms? Past the last luminous curl of the spiral arms, the galaxy doesn't stop. It simply dims. Clouds of cold hydrogen drift in faint threads. Lone stars wander in orbits so wide they take billions of years to complete. It's a region where the Milky Way becomes ghost-like, barely visible, yet still bound by the galaxy's gravity. If the bright spiral arms are the Milky Way's face, clear, structured, and full of detail, then this outer region is its whisper. A hushed transition between the familiar and the unknown. It is neither the chaotic halo above and below the disk, nor the well-lit lanes of star formation closer to the center. It is something quieter, a liminal zone, the galaxy's penumbra, where light fades into shadow and structure dissolves into near emptiness. From far outside the galaxy, if you drifted toward this region, you would first notice the thinning of stars. The sky would feel more open. Constellations that look dense and bright from Earth would stretch apart. The fabric of the Milky Way would loosen, revealing gaps between stars that grow wider with every light year you travel. Yet even here, gravity remains a gentle guide. Most of the stars you'd encounter in this outer territory are ancient, survivors from earlier eras of the galaxy's history. Their orbits trace immense paths, sometimes plunging inward toward the spiral arms, sometimes arcing outward into near darkness. They move through regions so quiet and empty that they may go millions of years without passing another star closely enough to notice. This is where the galaxy begins to blur. Maps of the Milky Way show the spiral arms fading into long, tenuous filaments of hydrogen gas. These cold flows are the galaxy's outermost breath, whisper-thin and almost invisible to human eyes. But with radio telescopes, tools that listen to the 21-centimeter emission of neutral hydrogen, astronomers can trace these filaments far beyond the visible disk. They stretch outward like pale fibers, marking the last traces of the Milky Way's organized structure. If you were to drift through one of these clouds, it would not resemble a cloud at all. There would be no light, no color, no sense of motion. The density is so low that you could travel for days without encountering a single molecule. And yet, in aggregate, these clouds make up a vast envelope of gas feeding the slow star formation happening closer in. They are the galaxy's quiet reservoir. Just beyond these faint threads lies another population, the outer disk stars that stretch farther than the spiral arms themselves. These stars, sometimes called the extended disk, follow orbits that seem almost impossible, huge loops that take them thousands of light years above the plane before they swing back downward, like stones thrown high in a slow arc. Their paths reveal something important. The spiral arms are not boundaries, they are patterns, waves, temporary gatherings of stars and gas. The disk continues long after the arms lose their brightness, and yet the brightness matters. In the outer regions, where star formation slows, the glow that defines a spiral arm fades. The materials needed to form new stars, dense gas, dust, turbulence, become scarce. What remains is older, dimmer, and more widely spaced. And so the Milky Way's rotation still holds these distant stars in its quiet grip. They orbit just as faithfully as the stars nearer the Sun, but over distances so large that a single revolution may take 10 times longer. Their motion helps reveal the unseen mass surrounding the galaxy. If only visible matter existed, these outer stars would drift away over billions of years. Their continued orbits are one of the strongest pieces of evidence for something larger, the dark matter halo stretching far beyond. In this sense, what lies beyond the spiral arms is not emptiness, but the first hint of the galaxy's invisible architecture. As you drift farther, another structure begins to appear, not in light, but in motion. Streams of stars, stretched thin like faint ribbons, curve through this region. They are remnants of dwarf galaxies long absorbed by the Milky Way. Their stars, tugged and stretched by gravity, continue to follow their ancient orbits as they slowly blend into the halo. These stellar streams tell a quiet story of the galaxy's past. Once, billions of years ago, the Milky Way was not alone. Dozens of small galaxies orbited it, many now torn apart. Their debris forms faint arcs and bridges of stars that wrap around the galaxy like forgotten trails. Some streams are so faint that only the most sensitive telescopes can detect them. Others, like the Sagittarius stream, carve dramatic pathways across the sky. To drift beside one would feel like meeting ghosts, stars that once belonged to a different world, now traveling through the Milky Way as permanent guests. As you move outward, the density of these streams decreases. The gravitational pull of the Milky Way weakens. You begin to sense a transition, not a wall, but a slow loss of structure. Stars still orbit the center, but their paths become less aligned with the disk. Some tilt at steep angles, others form long, looping ellipses that carry them into the halo. The galaxy is loosening. Beyond this point, the Milky Way no longer behaves like a flat disk, but like a diffuse sphere of ancient stars. This is the domain of the outer halo, a region where the concept of beyond the spiral arms becomes difficult, because the arms themselves have long since dissolved behind you. Yet you can still trace the influence of the disk. Its rotation echoes faintly in the motions of halo stars. Its light, though distant, still forms a soft, glowing band behind you. Even here, far from the bright spirals you know, the Milky Way's presence persists. But one more layer remains before the galaxy's gravity truly thins into the dark. At even greater distances, scientists have found ultra-faint dwarf galaxies, tiny companions orbiting on the edge of the Milky Way's reach. They are held loosely, like distant satellites circling a dim world. Their stars belong to the galaxy only in the loosest sense, bound by a gravitational thread so fragile that the tides of other galaxies might one day pull them away entirely. These dwarfs mark one of the outermost signs that you remain in the Milky Way's domain. And yet, even beyond them, the galaxy does not abruptly end. Instead, the dark matter halo continues, unseen but measurable, stretching almost 1,000,000 light-years across. It is here that the Milky Way's influence finally reaches its faintest echo, where the gravitational pull of neighboring galaxies becomes comparable to our own. This is the true frontier, not marked by light, but by balance. If you hovered in this place, halfway between two massive galaxies, you would feel almost weightless. Gravity would tug equally in opposite directions, neither pull strong enough to dominate. It is a quiet boundary, one defined not by what you see, but by what you no longer feel. And this is the answer hidden behind the question. What lies beyond the spiral arms is not a place where the galaxy ends, but a place where the galaxy softens, where starlight grows thin, where structure fades, and where the Milky Way becomes more suggestion than shape. As we drift deeper into this mystery, one question rises gently from the dark. If the spiral arms dissolve into these ghost-like regions, how far outward does the galaxy's stellar halo truly reach? Part 4. How far does the stellar halo reach? The stellar halo is the Milky Way's quiet whisper, an enormous sphere of ancient stars surrounding everything we know. These stars are sparse, fragile in their loneliness, but they extend tens of thousands of light-years beyond the visible disk. If you were to drift among them, space would feel almost empty, yet still gently threaded with starlight. Out here, far beyond the bright spiral arms, the galaxy doesn't look like a disk anymore. It feels more like a memory, diffuse, scattered, a trace of something that once burned brighter. The stars around you appear isolated, drifting in orbits so elongated and slow that they resemble the paths of comets rather than the neat circles found closer to the center. Some of these stars take billions of years to complete a single loop. Others wander in trajectories tilted at steep angles, passing above and below the galactic plane like long, slow breaths. This is the stellar halo, a vast, faint sphere stretching perhaps 300,000 light-years from end to end, embracing the galaxy in a soft, ancient glow. Yet to call it a sphere of stars is almost misleading. It is more like an echo, a field of scattered points left over from a younger, more turbulent Milky Way. Where the disk is full of dense clusters and luminous clouds, the halo is sparse, so sparse that the average distance between stars can be hundreds of light-years. If you were to search for a companion star, you might drift for lifetimes without finding one. And yet, the halo holds the oldest stories of the galaxy. The stars you see here were among the first to form, long before the Milky Way had spiral arms, long before the disk had settled into its graceful rotation. Their chemical signatures reveal a time when the universe contained almost no heavy elements, only hydrogen, helium, and a trace of lithium. These stars are fossils, not in the sense of being dead, but in the sense of preserving the conditions of the early cosmos. If you analyzed their light, you would find them lacking in carbon, oxygen, and iron, the elements forged in later generations of stars. Their simplicity is not emptiness, but age. Many of these ancient suns came not from the Milky Way itself, but from smaller galaxies that the Milky Way absorbed long ago. Over billions of years, as dwarf galaxies wandered too close, the Milky Way's gravity tore them apart. Their stars were pulled into long, thin streams, tidal remnants that now wrap around the galaxy like pale ribbons. As you drift through the halo, you might pass one of these streams. It would appear as a faint linear arrangement of stars, all moving in nearly the same direction. To your eyes, it might look like an accidental pattern, a chance line across the sky. But to astronomers, these are the fingerprints of cosmic cannibalism, the quiet merging of galaxies that built the Milky Way into what it is today. Some of these streams stretch over 100,000 light-years. Others loop around the galaxy multiple times, gradually blending into the background of the halo. In the dimness, they serve as threads tying the present to the past. As you drift farther outward, the stars become even more sparse. Now, you might find yourself in regions where a single star illuminates a volume of space larger than the region containing thousands nearer the center. The silence here is profound, the darkness nearly complete, yet gravity still binds everything. You can feel it in the paths of the stars, which always curve inward, even faintly, toward the heart of the galaxy. The stellar halo doesn't simply end at a specific radius. It thins, it fades. Eventually, the density of stars becomes so low that they are difficult to detect at all, even with modern telescopes. But even in that near emptiness, something remains. At around 150,000 light-years from the center, you reach the edge of what scientists often call the inner halo. Beyond this, the stars are even older, and their orbits even more chaotic. The outer halo, as it's sometimes known, is where the most metal-poor stars reside, true relics from the dawn of the galaxy. If you could listen to their histories, they would tell of a time when the Milky Way was young, when it was smaller and more turbulent, when nearby galaxies approached not as stable neighbors, but as potential collisions. These stars do not lie. Their orbits reveal that the halo once experienced violent events. A major merger about 8 to 11 billion years ago, called the Gaia-Enceladus event, sent waves of chaos through the young galaxy, reshaping its structure. Many of the halo's stars arrive during that collision, flung into vast looping paths that carry them far from the disk's orderly rotation. When you see these stars today, solitary, ancient, drifting, you're seeing survivors of that cosmic upheaval. But even these are not the outermost boundary. The stellar halo fades gradually into a region where stars are so few that the night becomes nearly indistinguishable from intergalactic space. And yet, as long as a star remains gravitationally bound to the Milky Way, it is part of the halo. The farthest confirmed stars orbit at distances approaching 300,000 light-years. Some possible candidates may lie even farther, out to 5,000 light-years, but these are difficult to measure and easy to confuse with stray stars belonging to neighboring dwarf galaxies. If you drifted this far out, the Milky Way would look delicate and miniature, a glowing spiral at the center of a vast ocean of dark. You would see the disk, the bulge, the arms, but all of it compressed into a faint image like a distant lantern. But the halo extends still farther in another form, not in stars but in dark matter. While the stellar halo stretches perhaps a few 100,000 light-years, the dark matter halo, the true gravitational boundary of the galaxy, extends nearly 1,000,000 light-years. It is invisible, but its presence is undeniable, shaping the motions of every halo star you've passed. In this sense, the stellar halo is only the inner skin of something much larger. The stars you see are tracers, like dust swirling inside a vast invisible sphere filled with mass we cannot see. The farther you drift, the more dominant this unseen mass becomes. Eventually, you reach a place where the Milky Way's pull weakens, where the gravitation of the nearby Andromeda galaxy begins to compete. This region, between the two giants of the local group, marks the edge, not through light but through balance. Here, the stellar halo fades into near nothingness. Only a few stars wander this far out, lonely travelers barely held by the galaxy's gravity. This is the frontier. Not a wall, not a cliff, but a quiet equilibrium between galaxies, a place where belonging becomes ambiguous, a place where the Milky Way's voice grows soft and the intergalactic dark begins its slow, steady rise. And as we continue drifting outward, one question begins to form like a distant star appearing through the haze. If the stellar halo rises outward in all directions, delicate and ancient, then what is the shape of the vast dark matter halo beyond it? And how does that invisible structure define the Milky Way's true reach? Part 5. What are the boundaries of the dark matter halo? The largest part of the Milky Way is something you cannot see. A vast halo of dark matter encloses the galaxy like an invisible shell, stretching nearly 1,000,000 light-years across. It is this unseen mass that gives the Milky Way structure, holding stars in their orbits and shaping the galaxy's true reach far beyond where light alone can guide us. If you could drift beyond the glowing disk, past the last wisps of hydrogen and the faintest stars of the stellar halo, the visible galaxy would eventually fade behind you. The bright spiral you know would shrink into a delicate swirl of light. And yet, even as its glow grew faint, its gravity would still hold you, still tug at your path, still shape your motion. That lingering influence, the way the Milky Way reaches into emptiness, is the signature of dark matter. In this region, the emptiness feels almost complete. No bright gas clouds, no spiraling arms, only the occasional elderly star drifting in silence. But the gravitational field around you does not match the faintness you see. It feels stronger than the visible matter can explain, too strong, too persistent, too deep. That discrepancy is the doorway into the dark matter halo. Dark matter is not a shadow, not a mist, not a hidden kind of star. It is a form of matter that does not emit or reflect light at all. It reveals itself only through gravity, and its presence becomes undeniable the farther you drift from the Milky Way's center. Out here, you feel its pull like a steady, patient hand guiding your motion through the void. To understand where this halo begins, you must step back inside the galaxy for a moment. Deep within the bright disk, stars orbit the center at nearly constant speeds, fast, steady, unchanging. If only the visible matter existed, these orbits would slow dramatically with distance from the core. The outer stars would drift outward, unable to keep pace with the gravity of the inner mass. But they don't drift, and they don't slow. Instead, the galaxy's rotation curve, the graph of orbital speed versus distance, stays almost flat. It is one of the most profound clues in astrophysics. It tells us that an enormous amount of unseen matter surrounds the galaxy, stretching far beyond the luminous disk. Without this invisible mass, the Milky Way could not hold itself together. So where do the boundaries of this dark halo lie? The truth is both simple and subtle. There is no sharp edge. Dark matter fades gradually, thinning with distance but never reaching a hard cutoff. Instead, its density decreases smoothly, like a fog dissolving over many miles. But astronomers do define a region where the dark matter halo becomes weak enough that external gravity begins to compete. This region is often called the virial radius. For the Milky Way, the virial radius spans roughly 800,000 to 1 million light-years, the distance at which the galaxy's gravity stops dominating its surroundings. Inside this immense sphere, the Milky Way's pull remains the strongest force. Beyond it, the tug-of-war with the Andromeda Galaxy and other members of the local group becomes more even. If you floated through this boundary, the shift would be quiet. You wouldn't feel a sudden change. There would be no wall, no barrier. But mathematically, the galaxy would begin to lose its grip on you. Your orbit, if you had one, would no longer be stable. You'd be a free agent between galaxies. But before you reach that distant frontier, there are several layers of the dark matter halo to pass through. The inner halo, extending out to hundreds of thousands of light-years, is relatively dense by cosmic standards. It shapes the orbits of halo stars, shepherds the paths of dwarf galaxies, and anchors the faint streams of stars torn from ancient mergers. It is textured, molded by billions of years of galactic collisions. Simulations show that these encounters create ripples, shells, and clumps in the dark matter, structures without light, silent patterns written entirely in gravity. If you moved through this region, you would notice it only through the motions of the stars around you. They would speed up or slow down subtly as you drifted through invisible lumps of gravitational mass. Farther out lies the outer halo, a more diffuse region where dark matter becomes smooth and quiet. This is where the density drops significantly, where the gravitational field begins to grow thin, and where individual stars become nearly non-existent. The few stars that do wander here are like lone lanterns in a vast, unlit desert. Yet even here, the dark matter halo remains wider than you might expect. Its reach is simply too large for the galaxy's visible boundaries to contain. The outer halo stretches so far that if you placed the entire luminous disk of the Milky Way beside it, the disk would look like a small coin inside a vast dome. But what truly defines the halo's boundary is not size. It is balance. At around 1 million light-years from the galactic center, a new pull becomes noticeable: the gravity of the Andromeda Galaxy. Andromeda's own dark matter halo extends outward with similar immensity. Just as the Milky Way reaches toward it, it reaches toward us. The two halos overlap slightly, creating a gentle gravitational tide between the galaxies. In this overlapping region, no galaxy can claim dominance. The gravitational field is shared, contested, blended. If you drifted here, you would be in a gravitational no man's land, suspended between two giants. It is not emptiness, it is the beginning of the local group. And this is where the Milky Way's dark matter halo, for all practical purposes, truly ends. But even this end is temporary. In about 4 billion years, the Milky Way and Andromeda will collide. Their dark matter halos will merge long before their stars do, creating a shared gravitational envelope that binds both galaxies into a single system. Long before the visible spirals touch, the dark halos will have already entwined. In this sense, the boundaries of the dark matter halo are not just about where the Milky Way ends, they are about where the next galaxy begins. The dark matter halo is also intertwined with the smallest companions of the Milky Way. Dozens of dwarf galaxies orbit within it, many residing deep inside the dark matter's gravitational well. These tiny galaxies are almost entirely dominated by dark matter themselves. Their motions, their shapes, and even their survival depend on the Milky Way's halo. Some of them orbit so far from the center, over 300,000 light-years, that they feel more like free-floating island universes. But as long as they remain within the dark halo's embrace, they remain connected to the Milky Way. The halo even governs the path of intergalactic gas. Streams of hydrogen drifting between galaxies bend gently as they pass through the halo, influenced by its gravity. These streams may someday fuel new star formation within the Milky Way, even though they originate far outside the visible disk. In this way, the dark matter halo is not just a boundary, but a bridge, connecting the galaxy to the broader universe, pulling in matter, shaping future generations of stars, defining what the Milky Way will become. As you drift near the halo's edge, the galaxy behind you becomes little more than a whisper of light. The stars grow faint, the spiral arms fade into the distance, yet the space around you remains structured by an invisible architecture, a gravity that still traces the outline of the Milky Way even when the light cannot. And as that invisible structure begins to thin, one question naturally follows, soft as a star disappearing over the horizon. If the dark matter halo defines the Milky Way's reach, then how do we know where its gravitational influence finally gives way, where our galaxy's pull ends and the pull of the universe begins? Part 6. How do we know the galaxy extends this far? Astronomers cannot touch the edge of the Milky Way, but they can measure its gravity. By watching how stars move, how fast they orbit, how gently they drift, they infer the presence of something larger holding them in place. Every motion becomes a clue, a faint signature of the galaxy's hidden boundaries. If you were drifting far beyond the spiral arms, watching the lone stars wander through the halo, the emptiness might fool you. Space would look bare, quiet, almost blank, but the motions of those stars would tell a different story. Each one follows a curved path, bending subtly toward the Milky Way's center. That faint curvature is the galaxy speaking, its gravity extending outward into regions where almost nothing shines. This is how astronomers map the unseen. They measure not the light, but the pull. The first hints of the galaxy's true size came from this kind of quiet observation. In the early 20th century, as scientists tracked the movements of stars far from the sun, they noticed something unusual. Stars that should have drifted away, too fast, too far, too lightly bound, somehow remained in orbit. Their paths were stable, even at immense distances from the galactic center. The visible Milky Way wasn't massive enough to explain this. The luminous matter, stars, gas, dust, did not provide enough gravity. Something else was holding these remote stars in place, something larger, something invisible. These motions became the first whispers of the dark matter halo, and they revealed that the Milky Way extended far beyond its bright disk. Today, scientists use a tapestry of methods to chart the galaxy's hidden boundaries. None of them touch the edges directly, but each one traces the shape of the invisible. One of the most elegant tools is the rotation curve, a plot of how fast stars and gas orbit at different distances from the center. If you could draw this curve yourself, drifting outward through the galaxy, you would expect the orbital speeds to drop as you left the bright core behind. That is how gravity behaves around smaller systems. Planets orbit slower the farther they are from their star. But the Milky Way's curve refuses to fall. Instead, it remains nearly flat. Even stars tens of thousands of light years out orbit just as fast as those nearer the Sun. This flatness is impossible to explain with visible matter alone. The only answer is that the galaxy's mass extends far, far beyond the luminous disk. A hidden structure, so large it defies intuition, must be shaping those motions. That structure is the dark matter halo. Rotation curves are powerful, but they are only one way to detect the galaxy's reach. Astronomers also study the motions of globular clusters, ancient dense swarms of stars orbiting the Milky Way like distant satellites. Some of these clusters lie more than 100,000 light-years from the center. Their velocities tell the same story. They are held firmly by a mass greater than what the eye can see. If the Milky Way ended at the spiral arms, these clusters would not remain bound. They would be drifting away into intergalactic space. But they don't drift. They orbit. Their obedience reveals the gravity that binds them, gravity from a structure extending far beyond the disk. Then there are the stellar streams, the fragile arcs of stars torn from ancient dwarf galaxies. These streams stretch across enormous distances, forming loops that encircle the Milky Way. Each stream behaves like a test particle, tracing the contours of the gravitational field. Their shapes reveal where mass lies, how it is distributed, and how far the halo extends. Some streams curve unexpectedly, pulled into graceful bends that only make sense if the Milky Way's mass stretches deeply into the dark. Others display slight asymmetries, hints of irregularities within the halo, clumps, waves, or echoes of mergers long past. In this way, the galaxy's edges become visible not in light, but in motion. Another method relies on the escape velocity, the speed a star needs to break free from the Milky Way's grasp. By studying stars moving unusually fast, astronomers can estimate how strong the galaxy's grip must be at different distances. These stars, some traveling hundreds of kilometers per second, act like probes. Their speeds set a minimum value for the galaxy's total mass, and the mass they reveal is enormous, far more than the luminous matter can explain, far enough that the Milky Way's halo reaches almost 1,000,000 light-years outward. Even the movement of satellite galaxies serves as a compass. Tiny systems like the Draco, Sculptor, and Fornax dwarfs orbit within the halo. Their paths, measured over decades, reveal the gravitational landscape they travel through. The large Magellanic Cloud, a dwarf galaxy in its own right, follows an orbit influenced not just by the visible disk, but by the vast, unseen halo. Its motion only makes sense when the halo's size and mass are accounted for. Every orbit tells the same story. Every path points to the same truth. The galaxy extends into regions where light fades entirely. Another quiet technique uses the distribution of hot gas in the halo. This gas is so thin it would be undetectable if not for the way it absorbs and emits X-rays. By measuring these faint signals, astronomers can determine how much matter is needed to hold the gas in place. The answer, again, is far more than the visible galaxy can provide. This gas requires a massive halo, a gravitational envelope so large that the Milky Way becomes only a bright core inside a vast sphere. But perhaps the most poetic method involves gravitational lensing. Even though the Milky Way's halo is not massive enough to create dramatic arcs like those seen around massive clusters, it still bends light subtly from background galaxies. By measuring these distortions, astronomers can map the dark matter's shape, even far beyond the regions where stars are found. It is a way of sketching the invisible, and the picture that emerges is not a sharp edge, Not a boundary with a fixed line, but a gentle fading of influence, a gravitational field that extends outward like a sigh. If you were floating out there, hundreds of thousands of light years from the center, you wouldn't feel the halo end. You would feel only the gradual lightening of the galaxy's pull, like the soft weakening of a tide. Eventually, as you drifted farther still, you'd reach a region where another force becomes familiar, the gravity of the Andromeda Galaxy, approaching across the void. The boundary between galaxies is not marked by light, but by balance. Even here, the Milky Way makes itself known. Its gravity competes, it whispers, it guides the faint motions of the few remaining stars. We know the galaxy extends this far because everything that moves, every star, every cluster, every cloud, moves within its unseen architecture. The dark matter halo is too large to touch, too quiet to observe directly, but its presence is imprinted everywhere. The galaxy reveals itself through motion. And as we follow those motions to their limits, a new question begins to take shape. If the Milky Way's gravity stretches so far, what marks the place where it finally yields, where another galaxy's pull begins to shape the stars drifting between them? Part 7. What happens at the edge of gravity's grip? There is a point where the Milky Way's pull begins to fade, where its gravity weakens and neighboring galaxies begin to tug back. This border, though invisible, is real, a quiet equilibrium between cosmic structures. If you could drift there, you would feel almost weightless between worlds. This region is unlike any other place in the galaxy. It is not the halo, where ancient stars still whisper their orbits around the center. It is not the disk, with its spirals and gas clouds and clusters glowing gently. It is something softer, an in-between realm where no single galaxy claims authority. Here, gravity becomes a negotiation. If you floated in this space, the Milky Way would appear small behind you, a delicate spiral, no larger than a coin held at arm's length. Its bright disk would be surrounded by a faint spherical haze, the stellar halo. Beyond that, a darker realm still, the unseen dark matter halo, extending outward like a vast invisible sea. Yet even this immense structure has limits. The farther you drift, the weaker the galaxy's grip becomes. The familiar pull that shapes every star, every orbit, every stream of light begins to soften. Your path no longer bends clearly toward the Milky Way. Instead, your motion becomes more ambiguous, more balanced, pulled in subtle ways by distant neighbors. You have reached the galaxy's sphere of influence, a boundary not of material, but of power. Astronomers call this region the Hill sphere, or sometimes the zero-gravity boundary of a galaxy. It is not a sharp line, but a gradual threshold where the gravitational influence of the Milky Way becomes comparable to the gravity of Andromeda, the next largest member of our cosmic neighborhood. The two galaxies, each surrounded by a dark matter halo, nearly 1 million light-years wide, extend toward one another like vast overlapping fogs. Between them lies a place where neither dominates. If you could place a small, weightless bead in this region and let it go, it would not fall inward toward the Milky Way, nor outward toward Andromeda. Instead, it would drift uncertainly, caught between two tides. It might hover for aeons, nudged only by the slightest imbalance. This is the frontier of the Milky Way's gravity. It is here that the galaxy's authority fades into the shared domain of the local group, a small cluster of galaxies that move through the universe together. Inside this group, gravity is communal. The Milky Way and Andromeda anchor the center, while dozens of dwarf galaxies orbit them like distant embers. To understand what happens at this boundary, imagine watching a lone star wander outward from the halo. For billions of years, its orbit has carried it deep into the galaxy's quiet fringes, but as it approaches this frontier, its path becomes unstable. A star moving too slowly will drift back toward the Milky Way. One moving too quickly may escape entirely, slipping into the space between galaxies, and one moving at just the right speed may fall under the influence of Andromeda instead. Every star at this boundary is a question. Which world will claim me? The answer depends entirely on gravity's delicate balance. Out here, the Milky Way's gravitational field is no longer smooth. Tiny irregularities, traces of long-ago mergers, create faint ripples that shape the motion of wandering stars. Dark matter clumps, relics of dwarf galaxies absorbed long ago, exert their own small tugs. Even the presence of satellite galaxies, such as the Large Magellanic Cloud, subtly reshapes the gravitational landscape, creating dips and rises barely perceptible but undeniably real. If you floated through this region, you wouldn't feel these ripples directly. Your body would sense nothing. But the paths of stars around you, slow drifting arcs stretching across hundreds of thousands of light years, would reveal that this place is not empty. It is a gravitational frontier textured by history. Yet the most striking feature of this region is its stillness. There are almost no stars here. The halo, already sparse closer in, becomes nearly vacant at these distances. You might see one lonely sun every few 100,000 light years. Sometimes you'd drift for months without encountering a single point of light. Space here feels vast in a way that even the halo cannot capture. It is a domain beyond structure, beyond familiar motion. And yet, paradoxically, this emptiness is defined by motion. The galaxy's true edge is not marked by light, but by the fading curvature of orbits. It is only by watching how objects move that astronomers know where this boundary lies. Distant dwarf galaxies trace the limits of the Milky Way's influence. Some of them, like Leo, move so quickly that they hover on the edge of escape, barely held by the galaxy's distant pull. Others follow paths so elongated that they carry them deep into the outer reaches before bringing them slowly back inward. These motions are like probes sliding along the edge of a bowl. Their behavior reveals the bowl's shape, even if you cannot see its contours. At the galaxy's true gravitational frontier, something remarkable happens. The Milky Way's pull and Andromeda's pull become equal. This balance point is not static. As Andromeda approaches us, moving at roughly 110 kilometers per second, the balance slowly shifts. Every million years, the gravitational frontier creeps closer to the Milky Way. Eventually, the two galaxies will merge, and this frontier will dissolve entirely. Their dark matter halos, already brushing against each other, will interlock long before the stars collide. When that happens, the quiet equilibrium you feel in this boundary will become a bridge, a shared gravitational field that melds two galaxies into one. But for now, the frontier remains a delicate quiet. If you hovered here and looked toward the Milky Way, you would see a shrinking spiral floating in the dark, a luminous coin held up against a black ocean. If you turned around, you would see Andromeda glowing faintly in the distance, its own spiral shape angled just slightly differently, like a companion lantern across a wide valley. Between the two lies a region where the universe itself seems undecided. The silence here is unlike any other silence in the cosmos. It is not the silence of deep space where stars simply do not exist. It is the silence of balance, a silence where two immense gravitational engines pull at you with equal strength, a silence where drift becomes indistinguishable from stillness. Here, the idea of belonging loses meaning. You are not in the Milky Way anymore, but you are not in Andromeda either. You exist in the gravitational pause between them. This boundary teaches astronomers something profound. Galaxies do not end where their light fades, they end where their influence yields. The Milky Way's true edge is not a circle of stars, nor a ring of dust, nor the perimeter of the halo. It is a place defined by competition, a soft handoff between two colossal structures. And as you drift in that quiet equilibrium, feeling neither pulled nor free, a new question emerges gently from the stillness. If this is the place where the Milky Way's gravity falters, then how do these boundaries shape the local group itself, this small congregation of galaxies woven together in the dark? Part 8. How does the Milky Way blend into the local group? Our galaxy is not alone. It is one member of a small cosmic family called the local group, a cluster of galaxies moving through space together. At its farthest reaches, the Milky Way's influence blends with that of Andromeda, their halos overlapping like two vast fogs drifting into one another. If you could hover somewhere between the two giants, far beyond the last stars of the Milky Way's halo, yet still long before you reach the luminous disk of Andromeda, you would find yourself in a strange kind of cosmic borderland. Not empty, not structured, but softly balanced. The gravity around you would no longer be dominated by a single galaxy. Instead, it would feel shared, as though the universe itself were holding two opposing weights in perfect suspension. This is the quiet place where the Milky Way dissolves into the local group. From Earth, the local group is difficult to imagine. We see only a handful of bright galaxies scattered across the night sky. Andromeda stretching faintly across one corner, the large and small Magellanic clouds glowing in the southern sky, and the rest too faint for the unaided eye. But the truth is that our galaxy resides in a cluster of more than 70 galaxies, most of them small dwarfs, held together by the combined gravity of the Milky Way and Andromeda. To understand how the Milky Way blends into this family, you must begin with the dark matter halos that surround each galaxy. These halos are not small shells wrapped around the bright parts. They are immense, stretching hundreds of thousands of light years in every direction. They are the true architecture of the local group, far larger and more influential than the luminous galaxies they contain. The Milky Way's halo, as you drift outward from the disk, fades imperceptibly into Andromeda's. There is no visible boundary, no line drawn in darkness. Instead, the transition is gradual, like the merging of two faint clouds. Their gravitational fields overlap long before their stars ever will. If you were drifting through this region, say, 600,000 or 700,000 light-years from the Milky Way, you might suddenly notice that the gravitational pull on you no longer points cleanly back toward the galactic center. Instead, it begins to tilt, to shift, to drift sideways. That shift is Andromeda's hand reaching across the void. The Milky Way does not end here. It simply becomes part of something larger, part of a shared gravitational environment. Inside this blended region, the motions of dwarf galaxies tell the story more clearly than words ever could. Some dwarfs orbit the Milky Way, some orbit Andromeda, and some hover between them, caught in a delicate tug-of-war. Galaxies like Leo Warn and Leo II drift along the edges of the Milky Way's gravitational influence, their paths shaped not only by our galaxy, but by Andromeda's distant pull. The members of the local group are not arranged neatly, but in a loose, drifting pattern, like seeds floating on intersecting breezes. At this scale, the individual identity of a galaxy begins to fade. What matters is not where the stars are, but whose gravity dominates their motion. And the local group itself has a shape. It is not a sphere or a disk, but a loose, flattened structure. Scientists sometimes call it a cosmic sheet, with the Milky Way and Andromeda forming its two largest anchors. The smaller galaxies cluster around them, forming something like two intertwined families moving inside a larger shared space. As you drift deeper into this region, an astonishing fact reveals itself. The Milky Way and Andromeda are not simply neighbors. They are on a slow, inevitable collision course. They are moving toward each other at roughly 110 kilometers per second. In cosmic terms, this is not a violent rush, but a long, slow convergence. Their halos already overlap. Their gravitational fields already mingle. The blending is not a possibility. It is ongoing, unfolding quietly across billions of years. The local group is not static. It is evolving. When astronomers trace the motions of galaxies throughout this region, they find patterns. Most of the dwarfs around Andromeda form a thin, rotating plane, a kind of cosmic disk of satellites tilted relative to the main galaxy. Some evidence suggests the Milky Way might have a similar structure. These planes of dwarfs may have formed when the two giant galaxies influenced one another early in their histories, their gravity sculpting the motions of the smaller galaxies around them. Even here, in this immense region between giants, the Milky Way's influence remains detectable. It shapes how gas flows between galaxies. It alters the trajectories of tiny dwarfs that wander too close. It helps carve the gravitational landscape of the local group. But so does Andromeda. The local group is a partnership, a shared gravitational architecture, a quiet collaboration between two massive galaxies drifting through the universe. As you drift outward from the Milky Way's halo, you enter a realm where the distances become almost surreal. The dark matter halo slowly thins, becoming less dense, until its influence is matched by the halo of Andromeda. Out here, the density of matter is low, but the gravitational geometry is rich. It is shaped not by local structures, but by the vast scale arrangement of the group. If you stopped in this region and released a small test particle, something weightless, untouched by light, the particle's motion would not simply fall toward one galaxy or the other. Instead, it might trace a complex path, bending subtly toward one mass at first, then shifting direction as it drifts closer to another influence. It might even hover, not truly falling, not truly escaping. This is the gravitational fabric of the local group. There is a point between the Milky Way and Andromeda where their pulls are equal. Astronomers call this a Lagrange-like equilibrium, not in the precise mathematical sense used for orbiting bodies, but as an analogy. It is a point of gravitational balance, a border between influences. In this balanced region, you feel neither galaxy pull with certainty. You feel the group. One of the remarkable things about the local group is its isolation. Beyond its boundaries lies a vast cosmic void, a region where galaxies are sparse, where gravity thins, where expansion dominates. The local group is like a small island of gravitational coherence surrounded by the ocean of universal expansion. Inside the group, gravity binds galaxies together. Outside it, space expands too quickly for small galaxies to join us. The local group remains coherent because its two largest members, the Milky Way and Andromeda, provide the majority of its mass. Their dark matter halos anchor everything, and as these halos slowly merge, the local group is transitioning toward its inevitable future, a single, larger galaxy that astronomers sometimes call Milkdromeda or Milkomeda, though any name is just a placeholder for something far beyond human timescales. Eventually, billions of years from now, the local group will no longer be a group at all. It will be a single gravitational structure. But today, it is still a family, a cluster, a quiet region where galaxies drift under shared influence. As you float through this region, the view in every direction is a reminder that galaxies are not solitary islands. They are participants in a cosmic neighborhood. The Milky Way fades into the local group not by disappearing, but by sharing space, sharing gravity with a larger structure. And as we drift deeper into this peaceful blended domain, a new question rises gently ahead. If the Milky Way blends into the local group so smoothly, then how do its smallest companions, its satellite galaxies, trace the true extent of its influence? Part 9. How do satellite galaxies mark the Milky Way's domain? Dozens of dwarf galaxies orbit the Milky Way, tiny companions circling a giant. They trace the edges of our galaxy's influence, moving like slow moons around a world of stars. Their faint paths help scientists map the Milky Way's outermost regions, revealing a gravitational reach far beyond the visible spiral. From the inside of the Milky Way, it is easy to forget these companions exist. Their light is dim, their stars few, their shapes often ragged from tidal forces that slowly peel them apart. And yet, these tiny galaxies, many no larger than a single bright globular cluster, play a crucial role in uncovering the true extent of the Milky Way. They are lanterns at the edges of our gravitational domain. If you could drift above the galaxy and look down from a distance of several 100,000 light-years, you would see the spiral disk shrink to a luminous whirlpool. Surrounding it, scattered like embers blown outward, are the dwarf galaxies, some clustered, some solitary, all locked in orbits so slow they take billions of years to complete. These systems are fragile. They contain only a few million stars, sometimes only a few thousand. but their orbits are wide enough and long enough to trace the Milky Way's gravitational contours in a way no star could. Astronomers often compare them to satellites around a planet, but the analogy is imperfect. Planetary moons orbit in tight circles bound by clear gravitational dominion. Satellite galaxies, by contrast, move through an enormous volume of space, often following paths that tilt steeply above and below the galactic plane. They travel through regions where the dark matter halo dominates, making them ideal test particles for measuring the true reach of the Milky Way. If you followed one of these dwarfs, say, the Sculptor Galaxy or Fornax or Carina, you would see how deeply the Milky Way's gravity extends. These galaxies do not orbit in neat circular paths. Instead, many follow elongated trajectories, moving slowly inward for hundreds of millions of years, then grazing the outer halo before curving back toward the dark. Their motions can only be explained by the presence of a massive, all-encompassing halo of dark matter that reaches far beyond the visible stars. Some dwarf galaxies lie deep inside this halo. Others skirt its edges, moving so quickly that they test the limits of the galaxy's hold. One example is Leo Virgo, a small, faint galaxy orbiting roughly 820,000 light-years from the galactic center. Its velocity is so high that astronomers once debated whether it might be breaking free, but detailed measurements revealed that Leo Virgo remains bound, barely, because the dark matter halo extends much farther than the visible disk would ever suggest. Leo Virgo, in many ways, marks one of the known outermost points where the Milky Way can still claim ownership. But satellite galaxies do more than reveal where the Milky Way's influence ends. They also show how the galaxy grew. Many of the dwarfs orbiting today are remnants of earlier mergers, survivors from smaller galaxies devoured by the Milky Way over billions of years. Their stars show age distributions and chemical fingerprints that differ from those of the Milky Way's disk or bulge, revealing that they were once separate systems. Some, like the Sagittarius dwarf galaxy, are currently being torn apart. Its stars form long streams wrapping around the Milky Way, leaving luminous trails that drift across the sky like quiet memories. If you could drift beside one of these streams, you would see the aftermath of galactic hunger. Ancient stars pulled into a thin ribbon, their orbits slowly stretched by the Milky Way's gravity. These tidal streams are themselves markers of the galaxy's domain. They show where the gravitational tides are, strong enough to unspool a galaxy completely. By mapping the shape and curvature of these streams, astronomers can trace the slope of the Milky Way's gravitational field, where it dips, where it rises, where unseen clumps of dark matter create small distortions. The Magellanic Clouds, the large and small Magellanic Clouds, are perhaps the most famous of the Milky Way's satellite galaxies. They are larger than most companions and visible to the naked eye from the southern hemisphere. For billions of years, they have orbited the Milky Way in a slow, sweeping dance, pulling long streams of gas behind them. These streams, known as the Magellanic Stream and the Leading Arm, arc across more than half the sky. Their presence tells astronomers that the Milky Way's grasp is not static. The orbits of these dwarf galaxies predict that the Milky Way's halo must be lopsided, slightly elongated, and more massive than once believed. The way the clouds move, how quickly they travel, how deeply they cut into interstellar space, provides clues to the halo's shape. Every satellite galaxy, every stream, every faint cluster on a long orbit carries a piece of the Milky Way's gravitational blueprint. Even the absence of galaxies in certain regions reveals something. Some directions around the Milky Way contain far fewer satellites than others, hinting at asymmetries in the halo's structure. A perfectly spherical halo would produce a more uniform distribution. Instead, we see patterns, subtle alignments, and planes of satellites that suggest the halo is more complex, shaped by billions of years of mergers, collisions, and cosmic interactions. If you could freeze time and draw all the orbits of the Milky Way's satellite galaxies as glowing lines in space, the image would look like a loose three-dimensional web surrounding the spiral disk. The lines would vary in thickness and shape, some sharp and looping, others slow and broad. Some would pass close to the disk, Others would drift deep into the outer halo. Together, they form a glowing boundary, a dynamic map of the Milky Way's true domain. The faintest dwarf galaxies are especially important. These ultra-faint dwarfs, discovered only in the last few decades, contain so few stars that they are nearly invisible. Some hold only a few hundred stars in total, but their existence at great distances confirms that the Milky Way's gravitational field extends farther than once imagined. Their survival, fragile as they are, means they must be held by the halo. If they were not, intergalactic tides would have stripped them apart long ago. Even the direction they move reveals the Milky Way's reach. A dwarf with a stable orbit must be bound. One with an erratic path, drifting too fast, might be an outsider merely passing through. These distinctions help astronomers refine their models. Every bound dwarf becomes a point on the map of the halo. Every unbound dwarf becomes a marker of where the galaxy ends. If you floated beside one of these small galaxies, say the Draco dwarf, you would feel the Milky Way's pull and the dwarf's smaller gravity blending around you. You might notice stars in Draco slowly spilling outward, forming faint arcs trailing in its wake. These arcs reveal how the Milky Way's tidal forces stretch and sculpt its companions. The dwarf galaxies are not merely orbiting, they are participating in the slow evolution of the halo. They provide the outermost sign that the Milky Way is not just a disk of stars, but a gravitational empire, vast, invisible, extending far beyond light. And as you continue drifting outward, guided by their paths, another question emerges with graceful inevitability. If the dwarf galaxies trace the edges of the Milky Way's domain, what lies beyond their orbits? Out in the silent realm where the galaxy becomes nothing more than a faint glow against the emptiness of intergalactic space? Part 10. What does intergalactic space look like? Beyond the dark matter, halo lies a realm with no name, intergalactic space. It is quieter than vacuum, colder than shadows, and nearly empty. Yet even here, tiny threads of gas and particles drift between galaxies, carrying the faint signatures of cosmic history across incomprehensible distances. If you could drift into this region, leaving the Milky Way slowly behind, you would cross a threshold unlike any other. One moment, the galaxy would still feel present, the faint pull of its gravity guiding your path, the dim shimmer of halo stars scattered through the dark. And then, gradually, almost imperceptibly, that influence would fade. The stars behind you would thin until they were no longer background points, but memories. The pull of the Milky Way would weaken to a whisper. You would enter a realm where distance becomes a language and silence becomes the landscape. Intergalactic space is not truly empty, but it is as close as the universe comes. If you opened your hand in this region and waited an hour, it is unlikely even a single proton would touch your skin. The density here is astonishingly low, far less than a single atom per cubic meter. The space between galaxies is nearly a perfect void, but not entirely. Even emptiness carries history. Faint wisps of hydrogen drift across these expanses. They are relics from the early universe, leftovers from a time long before galaxies formed, when matter was smooth and unstructured. Most of that primordial hydrogen has been pulled into galaxies over billions of years, collapsing into stars or clouds. But a small portion remains free, drifting through the void like dust suspended in sunlight, illuminated only by distant starlight or ultraviolet flashes from quasars. If you could see an ultraviolet, intergalactic space would reveal faint webs, delicate filaments of gas tracing an enormous structure known as the cosmic web. This web is the universe's skeleton, vast interconnected strands of dark matter and gas stretching across hundreds of millions of light years. Galaxies form along these strands like dew forming on spider silk. Even here, far beyond the Milky Way's reach, you are still inside this greater structure. The cosmic web shapes everything, even the emptiness between galaxies. Though you might feel alone in this void, the web binds you to a larger story. Far ahead, the Andromeda Galaxy glows faintly, a quiet lantern against the dark. It is the only bright object on the cosmic horizon, a reminder that even intergalactic space is not directionless. The Milky Way and Andromeda, bound by their shared gravity, drift through this space together. Their halos overlap slightly, but beyond those halos lies true intergalactic territory, a region between worlds. If you traveled outward long enough, leaving both the Milky Way and Andromeda behind, their shapes would shrink into faint smudges. The local group's smaller dwarf galaxies, Triangulum, Sculptor, Leo, Thorin, would become tiny flecks swallowed by the black. Eventually, the entire local group would compress into a miniature constellation, and you would float in the dark, stretching between galaxy clusters. Here, the silence grows even deeper. Intergalactic space is dominated by the universe's expansion. Every distant galaxy is receding from every other, carried outward by the fabric of space stretching between them. You would not feel this expansion directly. It acts on space itself, not on your body. But you would see it. The galaxies around you would drift apart over millions of years, slowly thinning into an even wider emptiness. This expansion is the quiet engine of intergalactic space. It is the reason the void remains the dominant structure of the cosmos. Yet, even in this expanding darkness, the faintest traces of matter remain. A lone atom might pass by every few meters. A photon from a quasar billions of years old might slip silently past you. A whisper of cosmic microwave background radiation, the afterglow of the Big Bang, might drift through your path. These leftover signals are incredibly faint, but they form a kind of cosmic echo. They tell you that even the darkest places are filled with memory. The temperature here is only a few degrees above absolute zero. Not because intergalactic space is cold in a conventional sense, but because there's nothing to warm it. Heat requires matter. And here, matter is almost absent. Only the ancient microwave glow, light stretched thin by the universe's expansion, gives this region its meager warmth. If you drifted long enough, you might encounter pockets of slightly higher density. These are residues of ancient gas clouds, or regions where the cosmic web's filaments are denser. In these places, intergalactic space becomes a quiet highway for particles. Hydrogen atoms, drifting for millions of years, may gather into sheets and rivers, pulled gently toward nodes of the cosmic web where new galaxies may someday form. Intergalactic space is not dead. It is waiting for gravity to sculpt it, waiting for galaxies to collide and reshape the web, waiting for the slow dance of cosmic evolution to continue. Occasionally, you might encounter a lone star wandering this space. These rogue stars are rare, perhaps one for every 100 billion stars born within galaxies. A few are ejected by gravitational slingshots during galactic collisions. Others are flung outward by the violent interactions of black holes. If you passed one, it would shine alone in the dark, an exile carrying its light through the emptiest reaches of space. The existence of these solitary stars is a reminder that intergalactic space is not separate from the universe's more structured regions. It is shaped by them. Every particle, every wisp of gas, every stray star comes from the same processes that built galaxies. They are the quiet outskirts of a cosmic system in constant motion. If you continued drifting outward, you would find that intergalactic space changes once again at larger scales. Eventually, you would feel the pull of gravity from an entirely different structure, the nearest galaxy cluster. The local group, small and modest, is only one island in a vast ocean. Beyond it lies the Virgo cluster, an enormous congregation of galaxies bound together by gravity far stronger than the local groups. Intergalactic space becomes less empty as you approach this region, not because matter is dense, but because the cluster's gravity has sculpted the void into streams and rivers of gas. In this way, intergalactic space is not uniform. It has texture, structure, flow. It is the quiet fabric connecting galaxies, clusters, and superclusters across unimaginable scales. And yet, the most striking thing about intergalactic space is still its stillness. Even though faint particles drift through it, even though ancient photons pass by, the overwhelming impression is one of gentle silence. Here, the universe reveals its true scale, not through what is present, but through what is absent. And as you float in this quiet darkness, one question begins to shimmer softly ahead. If intergalactic space is the great ocean between galaxies, then how far can the Milky Way's light travel into it? And what becomes of the photons that escape into this vast, silent sea? Part 11. How far does light from the Milky Way travel? A galaxy's reach can also be measured by its light. Photons leaving the Milky Way travel forever unless they strike something, a dust cloud, a distant star, or the surface of another world. In this sense, the galaxy's influence extends infinitely, carried on beams of starlight that never tire. If you could follow one photon as it leaves the sun tonight, one tiny packet of energy born in the core of our star, you would see a journey unlike anything else in the universe. First, it would pass through the solar system, slipping past planets and comets with no resistance. Then, it would drift outward through the galactic neighborhood, weaving through the thin web of dust and gas that fills the inner spiral arms. From there, it would rise out of the Milky Way entirely, leaving behind the luminous disk like a traveler stepping off the edge of a great continent into a silent sea. And then, it would keep going. This is the simplest truth about light. It is tireless. It does not slow down. It does not age. Unless something stops it, it will travel across the entire universe. So in one sense, the light from the Milky Way reaches infinitely far. But in another sense, the universe itself shapes how far that light can meaningfully travel. If you drifted far above the galactic disk and looked downward, the Milky Way would shine like a glowing whirlpool, hundreds of billions of stars illuminating a single structure. Yet the farther away you moved, the dimmer it would appear. The brightness of any light source decreases with distance, not linearly, but quadratically. Double the distance, and the brightness drops by a factor of 4. Move 10 times farther away, and the brightness fades by a factor of 100. This gentle diminishment means that even though photons travel forever, the galaxy's visible presence thins with distance until it becomes a faint whisper in the dark. After a few million light years, the Milky Way becomes a dim smudge. After tens of millions, it becomes a subtle glow. After hundreds of millions, it becomes a delicate point. And after a billion light years, its light would be indistinguishable from the cosmic background. But the photons are still there. They have simply been stretched by the universe itself. The cosmos expands as time moves forward, and as space expands, the wavelengths of photons grow longer. Blue light becomes red light becomes infrared light becomes microwaves. Eventually, the light from the Milky Way, especially the oldest photons, will be stretched so much that they blend into the slow hum of the cosmic microwave background. This transformation doesn't erase the photon's journey, it simply changes how we perceive it. If you could place yourself billions of light years away and look back toward the Milky Way, what would you actually see? That question depends not just on distance, but on time. A photon traveling for a billion years is showing you the galaxy as it once was, a younger structure, smaller, with fewer spiral arms, fewer stars, and perhaps a subtly different shine. Light becomes a bridge to the past. Every galaxy we see in the night sky is a window, not into the present, but into an earlier chapter of time. The farther we look, the deeper into history we peer. The Milky Way's light, too, is drifting outward into the cosmos, waiting to become someone else's ancient history, if anyone out there ever looks back. But aside from what light reveals to an observer, how far does it actually go? Imagine the photon from earlier, now drifting into intergalactic space. For millions of years, it may pass nothing but emptiness. Gravity does not slow it. Dust does not obstruct it. Even the faint hydrogen wisps of the cosmic web barely offer resistance. The photon crosses vast voids, passing between galaxy clusters like a silent runner moving through an empty desert. Occasionally, it might pass near a massive object, a black hole, a cluster, a massive galaxy. Gravity could bend its path slightly, a subtle curvature called gravitational lensing. But this bending does not slow the photon. It merely changes its direction, turning its path into a gentle arc before it continues outward. If the photon travels far enough, its wavelength begins to stretch due to the expansion of space. What began as visible light becomes infrared, then microwave, then eventually a long, faint radio wave, still traveling, still unchanged in its devotion to forward motion. In this way, the Milky Way's influence becomes eternal. Our galaxy's light will ripple across the universe long after the stars that produced it have faded. But most photons will never be seen by anyone. Most will wander forever through an empty cosmos. Most will outlive the stars, the galaxies, even the universe as we know it. In the far future, long after the Milky Way merges with Andromeda, long after their combined stars drift into new configurations, photons emitted today will still be moving outward, silent seeds of the past carrying the memory of what once existed. But there are other limits to consider. Some photons will strike matter. They may collide with a dust grain drifting between galaxies. They may be absorbed by a rogue molecule floating in the dark. They may encounter the outskirts of a distant galaxy, losing their energy to gas clouds or stellar atmospheres. Others may fall into black holes, vanishing not in the dramatic sense of being swallowed visually, but simply ceasing to contribute to the universe's visible light. But these are exceptions. Most photons remain forever unclaimed. If you could stand outside the universe, if such a place existed, and watch its history unfold, you would see light flow outward endlessly, like ripples expanding from a stone dropped into a cosmic lake. The Milky Way's influence is carried on these ripples, not its gravity, not its matter, but its radiance, its quiet whisper into the darkness. And yet, there is another limit beyond absorption and expansion, the concept of the cosmic horizon. Because the universe is expanding faster at greater distances, there comes a point beyond which light emitted today will never reach. That boundary is known as the cosmological event horizon. Anything beyond that horizon is being carried away faster than light can cross the expanding space. In practical terms, this means some photons from the Milky Way will never reach certain regions of the universe, not because they stop traveling, but because space itself pulls those regions away, faster than the photons can chase them. This is not a failure of the photon. It is a property of space-time. Still, within the observable universe, the Milky Way's light is free to wander. It can traverse galaxy clusters, cross voids, bend around dark matter halos, pass through cosmic filaments, and continue outward, aging only through the gentle stretching of its wavelength. In this sense, light is the Milky Way's most enduring export. Its stars burn briefly compared to cosmic time. Its planets evolve and fade. Its spiral arms shift shape. Even the galaxy itself will one day merge, dissolve, and transform. But its photons travel on. They are the messages of the galaxy, quiet, eternal, tireless travelers. And as you drift in this endless sea of light and dark, one final question emerges softly ahead, like a faint star rising over the horizon. If light travels endlessly, what do the stars themselves experience at the edges of the galaxy? Those few ancient suns that live so far from the disk that they barely feel the Milky Way at all. Part 12. What happens to stars at the galaxy's limits? Some stars live on the boundaries, wanderers with enormous orbits that stretch deep into the halo. Their lives unfold in isolation, far from the bustling spiral arms. To them, the Milky Way is little more than a distant glow, a faint reminder of the galaxy they call home. If you could drift beside one of these stars, silent companions in the vast outskirts, you would feel as though you were traveling with a solitary lighthouse keeper stationed on the edge of a cosmic continent. There is no crowd of neighboring suns, no dense clusters of starlight, no gas clouds drifting quietly past. There is only darkness and a single star holding vigil. These stars are often called halo stars, and they are profoundly old. Many were born when the galaxy itself was in its infancy, before the spiral arms had taken shape, before gravitational interactions sculpted the elegant form we know today. Some were captured from dwarf galaxies long since consumed by the Milky Way, fossils of galactic collisions scattered across the outer reaches. Their orbits are vast, looping ellipses that can stretch hundreds of thousands of light years from the galactic center. A single orbit might take billions of years to complete. In terms of human time, their paths are effectively eternal. If you followed one of these ancient travelers on its long journey, you would witness a life shaped by distance. When the star swings closest to the galaxy, it briefly passes through the denser regions of the halo, brushing against faint streams of stars torn from past mergers. When it drifts back outward, the Milky Way shrinks behind it, compressing into a glowing haze, only slightly brighter than the surrounding night. For most of its existence, this star sees its home galaxy as a distant smudge, beautiful, delicate, but far away. Life for a star on the outskirts is defined by solitude. Its nearest stellar neighbor may lie dozens or even hundreds of light years away, a distance so great that the night sky surrounding it would feel nearly empty. If planets circle such a star, their skies would contain no bright constellations, no dense patches of starlight, no luminous arcs marking spiral arms. A planet here would see the Milky Way as a faint band across the sky, no brighter than a distant cloud of light. The constellations known on Earth would vanish, replaced by a sparse scattering of stars whose arrangement changes only over geological time. To live on the galaxy's edge is to live beneath a sky of almost pure darkness. But despite their isolation, these stars are deeply important. They are windows into the Milky Way's past, its mergers, its chaotic adolescence, its ancient growth. Their motions trace the shape of the dark matter halo, because the farther they wander, the more sensitively their orbits respond to the mass enclosed within their path. A halo star's orbit is a kind of cosmic seismograph registering the invisible contours of the galaxy. If the dark matter halo were smaller, these orbits would change. If the halo were lopsided, the orbits would twist. If unseen dwarf galaxies lurked in the dark, the paths of these stars would wobble in detectable ways. Astronomers study these motions with extraordinary precision. By watching how halo stars accelerate and decelerate along their paths, they infer how much mass lies within their orbit. Some stars travel so far outward that their motion is governed not only by the Milky Way, but by the influence of the local group itself. For these fringe stars, the Milky Way is not the entire gravitational story. Another remarkable thing happens at the galaxy's limits. The boundaries become porous. The most extreme halo stars occasionally escape the Milky Way entirely. Their speeds, boosted by gravitational interactions deep inside the galaxy, can push them beyond the escape velocity of the halo. Once free, they drift into intergalactic space, becoming rogue stars, silent exiles journeying through the void. These hypervelocity stars are rare, but they are real. Some were flung outward by interactions with the Milky Way's supermassive black hole. Others were ejected by the gravitational slingshots of merging galaxies or disrupted star clusters. A few may have been captured from passing galaxies and now wander the halo in unstable orbits. A star at the edge of escape is like a traveler pausing at a border, deciding whether to remain or leave entirely. If you could watch one over millions of years, you would see the balance gradually shift. Its orbit would stretch, its velocity would rise. Eventually, it would drift past the gravitational frontier, past the point where the Milky Way's pull and the local group's expansion meet. After that, the star would be truly alone, traveling forever into the dark. But most halo stars do not escape. They remain bound, even in the Surya outermost regions. They are, in a strange way, guardians of the galaxy's past. Many hold chemical signatures so primitive that they reflect conditions close to the Big Bang. They contain fewer heavy elements than nearly any other stars. Some are among the oldest known, forming before the Milky Way had its first major mergers. These relic stars are clues to the galaxy's earliest populations, long vanished from the galactic disk. Halo stars also reveal the Milky Way's gravitational asymmetry. Their orbits are not randomly oriented. Many belong to coherent structures, streams, shells, and remnants of ancient dwarf galaxies. When you drift beside one of these stars, you might realize its neighbors, though faint, are moving in similar directions. They once belonged to the same small galaxy, torn apart by the Milky Way's tides. These streams stretch for tens or hundreds of thousands of light years, tracing graceful arcs across the dark halo. They are elegant markers of the galaxy's boundaries, written not in light, but in motion. Some halo stars were once part of galaxies like Gaia Enceladus or the Helmy streams, ancient mergers that fundamentally shaped the Milky Way's structure. Others belong to smaller, quieter acquisitions, dwarfs like Sagittarius, which is still being consumed and whose stars now form long rivers wrapping around the disk. To wander with one of these stars is to follow the fossil record of the Milky Way's growth. But what about life for the stars themselves? Do they evolve differently because of their remote environments? In some ways, no. Their internal physics is identical to stars anywhere. Nuclear fusion burns just as steadily. Their temperatures and lifetimes follow the same patterns as stars in the disk. But their surroundings change their fate in another way. These stars rarely encounter other stars, clouds, or disruptive events. Their environments are quiet, stable, uneventful. A halo star may live out its entire existence without ever passing close to another luminous object. Even at the end of its life, when it swells into a red giant, sheds its outer layers, and contracts into a white dwarf, nothing around it will disturb its transformation. It will die alone beneath an empty sky. The faint nebula it leaves behind will expand silently until it dissipates into the halo. No nearby stars will illuminate it. No planetary systems will wander through it. It will dissolve unnoticed, becoming part of the diffuse material that adds subtle texture to the galaxy's outskirts. Even in death, a halo star embodies solitude, but not insignificance. Each one holds a memory of the Milky Way's formation. Each one traces the invisible structure of the halo. Each one, in its quiet remoteness, marks the outermost boundary of what it means to be part of a galaxy. And as you drift beside these ancient wanderers, a final question takes shape in the darkness, gentle and inevitable. If stars can live so far from the heart of the galaxy, what lies beyond them? What is the true final measure of the Milky Way's reach into the cosmic deep? Part 13. How will the Milky Way's boundaries change over time? Galaxies evolve slowly, their shapes rearranging over billions of years. Stars drift outward, gas clouds collapse inward, and dark matter shifts like unseen weather. The Milky Way's edge is not fixed. It breathes, it grows, and eventually it will merge with Andromeda, reshaping its boundaries completely. If you could watch the Milky Way from far above, observing not across a human lifetime but over cosmic ages, the galaxy would appear far more fluid than static. The spiral pattern we see today is not permanent. Its arms are waves of density, not rigid structures, and they change with time. Stars move into and out of these arms like particles caught in a slow tide. The halo expands and contracts as new material joins, while older stars drift progressively outward. A galaxy, in its deepest nature, is a long, quiet motion. At the edges where gravity is weakest, this motion is most profound. The boundary of the Milky Way, so faint it cannot be seen, is constantly being reshaped. Tidal forces from distant galaxies tug at its outskirts. Dark matter streams from ancient collisions ripple through its halo. And inside the galaxy, the births and deaths of stars subtly redistribute mass, changing the gravitational balance. Every process, small or large, adds up over billions of years. One of the most significant long-term changes comes from stellar migration. Stars rarely remain at the same distance from the center forever. Over time, their orbits can shift outward or inward as they interact with spiral arms, gas clouds, and gravitational perturbations. Some stars wander gradually toward the galactic outskirts. Others fall inward, joining the denser regions near the disk. As these motions accumulate, the visible shape of the Milky Way slowly expands. The edge becomes less a fixed line and more a drifting frontier. It is not only stars that reshape the boundaries. Gas, mostly hydrogen, moves through the galaxy in enormous cycles. Some clouds collapse into new stars, reducing the gas in the disk. Others are blown outward by supernova explosions or black hole jets. Over millions of years, this outflow enriches the halo with thin streams of gas. Eventually, some of it cools, falls back inward, and becomes fuel for new generations of stars. These cycles push and pull the boundary like a slow breath. Dark matter, the invisible skeleton of the galaxy, also shifts over time. It is not static. Though it interacts only through gravity, its distribution can change subtly as dwarf galaxies merge with the Milky Way, as tidal streams stretch across the halo, and as gravitational interactions nudge different regions of the halo into new configurations. Over billions of years, these changes create soft ripples in the dark matter, altering the shape of the galaxy's gravitational field, and therefore its reach. But the most dramatic future reshaping comes from a cosmic inevitability. Andromeda is approaching. For billions of years, the Milky Way and Andromeda have drifted toward each other through the quiet of intergalactic space. Their halos already overlap, their gravitational fields already mingle. Within 4 to 5 billion years, their centers will meet, and the merger of the two galaxies will begin in earnest. This merger will be slow, elegant, and transformative. If you could watch it unfold, you would see the galaxies approach gently, not smashing, not colliding like solid objects, but passing through one another in great tidal sweeps. Their stars would mostly glide past without colliding. Their gas clouds, however, would compress, triggering waves of star formation. Their halos would blend into a single, massive sphere. The boundaries of the Milky Way would no longer be recognizable. As the merger continues, tidal tails, long streams of stars, would be pulled outward into space. Some of those stars might be flung so far away that they exit the resulting galaxy entirely. Others would form wide loops that eventually spiral inward again. The final result of this cosmic dance would be a new, larger galaxy, a giant elliptical or lenticular system astronomers call Milky Way. Its boundaries would extend far beyond the current reaches of the Milky Way or Andromeda, and its shape would be smoother and rounder. The spiral arms would fade. The new galaxy would be dominated by a broad spheroid of stars surrounded by a much larger dark matter halo. The local group would be reshaped as well. The dwarf galaxies currently orbiting both giants would fall into the newly merged system over billions of years, adding their stars to the growing halo. The boundaries of the new galaxy would swell as its gravitational influence deepened. But this merger is only one chapter of a longer story. Far in the future, tens of billions of years ahead, the universe will become increasingly dominated by dark energy. Cosmic expansion will accelerate. Distant galaxy clusters will drift farther and farther away, eventually disappearing beyond the cosmic horizon. The merged Milky Way galaxy will become, in practical terms, the entire visible universe for any inhabitants within it. Its boundaries, once shaped by neighbors, will be shaped only by itself. As expansion accelerates, intergalactic space will widen. The vast void beyond the galaxy will become quieter, emptier, colder. Fewer dwarf galaxies will fall inward. Eventually, the local group structure will dissolve into a single gravitational island, isolated in an expanding sea. Inside Milky Way, new stars will continue to form from the remaining gas for a while. But eventually, the star formation rate will slow. Gas supplies will dwindle. The galaxy will grow dimmer. Over trillions of years, the brightest stars will burn out. Only long-lived red dwarfs and cooling white dwarfs will remain. The boundaries of the galaxy will still exist, but they will no longer glow. Only dark matter will remain as the framework holding the system together, along with the few surviving stars flickering like embers in a cooling hearth. Still, even then, the galaxy's boundaries will continue to change. Dark matter will slowly diffuse. Rare stellar encounters will shift orbits. Occasional collisions between dwarf remnants will create gentle gravitational disturbances. The galaxy that emerges in the far future will be quieter, simpler, and more diffuse than anything we see today. If you could drift to its outer edges in that distant time, you would see little more than a faint cold haze of ancient stars, each separated by unimaginable distances. The core would be a small, glowing knot far behind you. Everything else would be darkness, but the galaxy would still exist, its gravity would still hold, and its boundaries, once sharp, once dynamic, once shaped by the long dance with Andromeda, would now be defined by the slow cooling of the universe itself. In this sense, the Milky Way's edge is not a place, it is a process. A slow evolving line shaped by time, gravity, and the quiet breath of cosmic change. And as we drift deeper into these future possibilities, a gentle question arises. If the Milky Way's boundaries shift with time, then what final shape does the universe itself impose? And what will the galaxy ultimately become in the deep, distant future? Part 14. How do black holes influence a galaxy's size? At the center of the Milky Way lies a supermassive black hole, but it is not the only one. Tiny black holes drift throughout the galaxy, remnants of ancient stars. Their gravity, though small compared to the entire structure, contributes to the quiet architecture of the galaxy's reach. If you could float above the galaxy, hovering in the silence of the halo, you would see the Milky Way as a softly glowing disk. The luminous stars, the swirling spiral arms, the faint haze of scattered dust. These are the features that define our idea of a galaxy. But beneath this visible beauty lies a deeper structure. It is shaped not only by gas and stars, not only by dark matter, but also by countless black holes moving quietly throughout the galaxy's vast reaches. Their influence is subtle, but over billions of years, subtlety becomes structure. At the heart of the Milky Way, the supermassive black hole, Sagittarius A, anchors the central bulge. 4 million times the mass of the Sun, it sits in the crowded core like an invisible engine, shaping the motions of stars in its immediate vicinity. But despite its immense mass, Sagittarius A does not dominate the galaxy. It influences only the innermost region, about a few tens of light years across. Beyond that, the gravitational pull of the galaxy's stars, gas, and dark matter far outweigh the central black hole's grip. Yet that small influence is precise. It organizes the central region, ensuring the dense cluster of stars remains stable. It carves out the orbits of the stars nearest to the core. It shapes the distribution of matter that eventually forms the bulge. Every stable galaxy has a supermassive black hole at its center, and these objects help galaxies anchor their cores. Without them, the centers of galaxies might be more chaotic, more susceptible to disruption from early collisions. The black hole's gravity provides a kind of gravitational focus, a point around which the inner galaxy can organize. But the Milky Way's true size, its enormous halo, its farthest boundaries, is shaped by much more than just this central mass. To understand the black hole's influence on the galaxy's reach, you must travel outward, much farther outward, because scattered throughout the Milky Way are hundreds of millions of smaller black holes, stellar mass remnants left behind when stars 20, 30, or even 100 times the mass of the Sun died. These black holes are invisible travelers. They drift through the galactic disk, through clusters, through the halo. Some travel alone, others move as pairs, locked in slow orbits. A few are caught near massive gas clouds, altering the paths of dust and hydrogen around them. Each one exerts a gravitational influence, tiny on its own, but meaningful when multiplied across the galaxy's lifetime. When a massive star collapses into a black hole, its mass is not lost. It simply becomes concentrated. That mass remains part of the galaxy's gravitational field. Over billions of years, the distribution of these remnants, along with neutron stars and white dwarfs, contributes to the galaxy's gravitational architecture. At the scales of stars and star clusters, black holes reshape local environments. They affect how clusters evolve, how stars interact, and how gas flows. But on larger scales, their influence blends into the galaxy's gravitational field, adding weight where visible starlight may not reveal it. Imagine drifting through the disk, a black hole the size of a city. Small, dark, undetectable except by gravity, passes silently a few light years away. You feel nothing, but a nearby star does, Its orbit adjusts slightly, quietly, over thousands of years. Multiply this by millions of black holes spread across billions of years, and you begin to see how these objects can subtly shape the galactic structure. Their gravitational nudges accumulate. Their presence redistributes mass. They influence the dynamics of star clusters, thickening parts of the galactic disk and adding complexity to the halo. Even in the far outer regions, black holes contribute. Some black holes are thrown outward by gravitational slingshots, ejected from star clusters or binary systems at significant speeds. These exiled black holes travel into the halo, becoming dark wanderers at the edge of the galaxy. They are difficult to detect, but their mass is real, and their gravity adds to the overall structure of the halo. In the faint outskirts of the galaxy, where stars are rare and the dark matter halo dominates, a drifting black hole becomes a quiet clue to the Milky Way's evolutionary history. If you could map every such remnant, you would reveal the fingerprints of ancient mergers, disrupted clusters, and the long, slow diffusion of stellar remnants into the halo. But there is another way black holes shape the galaxy's size, not by adding mass, but by removing it. When black holes merge, especially when two massive ones collide, they release energy in the form of gravitational waves. These waves carry mass energy away from the region, subtly reducing the local gravitational field. While this effect is incredibly small on galactic scales, it is part of the universe's gradual redistribution of energy. The Milky Way's central black hole may also grow as it consumes gas and dust. When it does, it releases powerful jets and winds of radiation. These outflows can push gas outward, heating it, thinning it, and preventing it from collapsing into new stars. Over time, this feedback shapes the star formation rate in the galaxy, influencing how quickly the visible disk grows or fades. A black hole, though silent by nature, can influence the galaxy's brightness. But the most profound connection between black holes and the Milky Way's size lies far in the future. When the Milky Way collides with Andromeda, the supermassive black holes at the centers of each galaxy will eventually merge. The result will be a single, even more massive black hole at the heart of the new galaxy. The merger will send gravitational waves rippling through the fabric of space, briefly reshaping the central regions and redistributing mass. This new black hole will become the anchor for Milky Way, the future galaxy formed from the merger. At the same time, the outskirts of the galaxy, the halo, will expand through tidal interactions. Stars will be flung outward into enormous loops. Some will escape. Others will form elongated streams. The influence of the central black holes will ripple outward, indirectly shaping the final distribution of mass. In this way, black holes help determine the future size of galaxies, not by directly pulling material into the halo, but by shaping the flows of gas, the stability of the core, and the gravitational dynamics of the merger. Their influence reaches farther than their event horizons, farther than their accretion disks, farther even than the regions where they shape star orbits directly. They influence the galaxy by anchoring its center, guiding its evolution, and participating in the cosmic events that determine its future reach. At the smallest scales, they act as quiet sculptors. At the largest scales, they become anchors for entire galaxies. Even the black holes wandering the halo, lonely, invisible, wandering through darkness, contribute to the Milky Way's total mass. They help determine how far the galaxy's gravity can reach into intergalactic space. In this sense, every black hole, large or small, is part of the galaxy's architecture. And as you drift deeper into this understanding, another question begins to emerge softly, like a faint glimmer rising on the horizon. If black holes quietly shape the boundaries of the Milky Way, then what does the galaxy look like when it is reduced to its deepest structure, when only its invisible framework remains? Part 15. Is there truly an edge at all? When you zoom out far enough, the idea of an edge dissolves. The Milky Way is not a wall, but a gradient, a long, soft fading of structure into the wider universe. Its boundaries depend on what you measure: stars, light, gas, gravity, or dark matter. Each tells a different story, each draws a different line. If you stood somewhere far from our galaxy, far beyond the halo, Beyond the reach of most stars, beyond the delicate shells of gas drifting outward, you would look back and see something that defies the simplicity of borders. You would not see a cutoff point where the Milky Way suddenly stops. Instead, you would see a slow thinning, a dimming, an unraveling of structure until the galaxy becomes a single spark against an ocean of darkness. Edges, in a cosmic sense, are not places. They are transitions. The luminous disk has a shape you can sketch, a thin, glowing spiral about 100,000 light-years wide. That is one kind of boundary, the visible one. But if you follow the stars outward, you will find that they do not stop neatly at the edge of the disk. They trail off into the halo, becoming fewer and older. This faint population of ancient stars stretches out for hundreds of thousands of light-years, long past where the eye feels comfortable calling something a galaxy. If you instead measure hydrogen gas, you find a different boundary. Cold clouds of neutral hydrogen reach far beyond the spiral arms, sometimes extending to twice the diameter of the visible disk. These clouds are patchy, fragmented, delicate, threaded into the halo like faint drifting mist. They trace an outline that is wider than the stellar distribution, but narrower than the dark matter halo. Measure light, and the story changes again. Photons travel forever. There is no edge in light. The Milky Way's radiance pours outward into the void endlessly, thinning with distance, stretched by cosmic expansion, but never coming to a hard stop. If you measured gravity, the boundary grows still larger. Gravity has no edge. It doesn't end. It simply wanes. Even at 1,000,000 light-years from the galaxy's center, the Milky Way's gravitational pull is still present, though faint. Beyond that, its influence blends with the pull of Andromeda, and the two giants share a gravitational field. Their halos overlap like two fog banks merging in a night sky. If you measured dark matter, the contour grows wider still. The Milky Way's dark matter halo stretches nearly 1,000,000 light-years in all directions, forming a sphere so vast that the luminous disk inside it looks like a small coin resting at the center of a soap bubble. Yet even that halo does not end abruptly. It merely becomes too diffuse to define. So what, then, is the galaxy's edge? Perhaps the better question is, an edge for whom? If you are measuring the reach of gravity, the galaxy has no boundary. If you are measuring starlight, the boundary is soft and subjective. If you are measuring gas, it becomes a shifting, uneven frontier. If you are measuring dark matter, the boundary is almost philosophical. If you are measuring the region where the Milky Way dominates the local group, the edge lies near the point where Andromeda's pull becomes equal. Each perspective carves the galaxy differently. This is why defining an edge becomes almost an act of interpretation rather than measurement. The Milky Way is not a single structure, but a nested collection of structures, each one extending a different distance, each one forming a different part of its identity. Think of the galaxy as a series of spheres and layers. At the center, a supermassive black hole anchoring the core. Around it, the dense bulge. Then, the thin disk with its spiral arms. Beyond that, the thick disk. Then, the stellar halo. Then, the tidal streams from swallowed dwarf galaxies. Then, the cold hydrogen envelope. Then, the dark matter halo. Then, the region where gravity blends with Andromeda. Then, the local group itself, drifting through intergalactic space. Where in that sequence does the galaxy end? It depends on which layer you decide represents its essence. If you are someone looking from the inside, from a planet beneath a sky, your instinct might be to define the Milky Way by its light. The glowing ribbon we see across the night is our most immediate experience of the galaxy. But that ribbon is just the disk, just one layer. It is the most vibrant, the most visible, but not the whole. If you follow the path of stars, the galaxy becomes larger. The halo stretches so far that it challenges the idea of belonging. A star 200 light-years from the center is still part of the Milky Way, even though it drifts in near emptiness. If you follow the gas, the galaxy becomes even more diffuse. The hydrogen envelope reaches far beyond the bright regions. It threads outward like smoke dissolving in the air. If you follow gravity, the boundary dissolves almost entirely. Gravity cares little for edges. It extends wherever mass exists. It merges with the gravity of neighboring galaxies, blending structures into a shared field. If you follow dark matter, the boundary becomes so large and so soft that the idea of an edge loses meaning altogether. Perhaps this is the truth hidden beneath all the others. A galaxy does not end. It transitions. The Milky Way transitions into its halo. The halo transitions into the local group. The local group transitions into intergalactic space, and intergalactic space transitions into the cosmic web. Even the cosmic web transitions into deeper voids and other structures beyond. Edges are conveniences, mental frameworks that help us describe something fundamentally continuous. And yet, there's still beauty in trying to define a boundary. Because in doing so, you reveal something about the galaxy itself. If you choose the outermost stars as the edge, you emphasize the story of ancient wanderers, relics of long-ago mergers. If you choose the hydrogen envelope, you reveal the slow breathing of the galaxy's gas. If you choose the gravitational boundary, you highlight the Milky Way's relationship with Andromeda and the local group. If you choose the dark matter halo, you show the invisible skeleton that holds the entire structure together. Each choice traces a different truth. Each truth is real. Each edge is valid in its own way. The galaxy is a gradient, not a cliff. To ask where it ends is to choose which part of its identity matters most. And if you could stand at any of these boundaries, on the edge of the stellar halo, or on the edge of the hydrogen cloud, or on the edge of the dark matter domain, it would not feel like a border. It would feel like a soft fading, a thinning, a quiet drifting into a larger environment. The Milky Way does not end where its structure stops. It ends where your definition does. If you define it by what you can see, the edge is close. If you define it by what you can measure, the edge is far. If you define it by what you can feel, the edge dissolves entirely. Because the galaxy is not a thing with an outline. It is a process, a history, a gravitational conversation across billions of years. And as we arrive gently at the close of this exploration, a final question rises like a soft echo from the dark. If the Milky Way has no single edge, then how do we, who live inside it, make sense of our place within something so vast and boundaryless? The Milky Way is not a fixed thing. It is not a circle in the sky, nor a neat shape you can hold in your mind. It is a gradient of motion and age and gravity, a softly woven structure that fades into larger and larger environments. From the bright spiral arms where new stars are born, to the ancient halo drifting in silence, to the vast dark matter sphere embracing everything we know, the galaxy is a continuum, a quiet, unfolding across unimaginable distances. You live deep within this structure, carried by its rotation, held by its gravity, shaped by its history. Even as you sit still, you exist inside a living system, a cosmic motion that began long before humanity took its first breath. You are part of a galaxy whose light stretches forever, whose stars wander in long arcs, whose boundaries dissolve into deeper realms of the universe. And when you zoom out far enough, you find that there was never an edge at all, only layers of belonging, gently blending into one another. So as you drift toward rest, breathe into that perspective. The universe is vast, but you are woven into it. You belong to a galaxy that has no sharp borders, no hard walls, only quiet transitions that fade into calm. Thank you for being here tonight and for letting this quiet journey accompany you. If this gentle exploration brought you even a moment of peace, your soft like or a quiet tap on subscribe means more than you know. Rest well, settle into the stillness, and let the soft glow of the Milky Way carry you into sleep.